Okay. Thank you. Thanks a lot for the introduction and also for the opportunity to being here talking about the basics of biomedical circuits. So something that we need to do now is to switch a bit gears. We will move from the digital world to the analog world. So you have seen how wonderful digital design is with a lot of level of abstraction, automatic generation. That doesn't happen in analog design. So in analog design, you will have to care about every single element of your circuit, all known idealities. You need to trace them back to all the components, to all the sub-circuits, and also at system level. So it's a little bit more complex to think of analog design when it becomes very, very complex. So self-introduction, I'm Carolina. I'm originally from Colombia. I did my postgraduate studies in Europe. Specifically, my PhD was done in Leuven in Belgium in collaboration with IMEC. And since then, I have been working at IMEC through different roles, always involved in research of biomedical circuits and sensor interfaces. I have been appointed to many conferences in circuit design. I'm very interested also to interact with young students. And I'm hoping that today I can give you some insights into these basics of biomedical interfacing because I find this a very, very beautiful application of electrical engineering. So to start, our human body is actually a fantastic biological machine. When things go wrong, it is very amazing that we can access many of our vital parameters from outside of the body through electrical and optical methods. We can use this ability to actually build many wearable and implantable technologies that require system, circuit, and algorithm innovations to impact many fields. I cannot advance. I like this. Yeah. To impact many domains of medicine. And we can do this to, for example, manage chronic diseases, to do diagnosis, or even in primary prevention. So when we want to create these interfaces between the biology and technology, we need to think first of dimensions. With the advances of lithography, micro and nanolithography that we have now, we can actually fabricate silicon interfaces or silicon pieces that have similar dimensions as biology components, such as blood cells, bacteria, antibodies, and even DNA. And this is very important because it gives us opportunities to create these interfaces at very different levels. But not only the dimensions are important, as Ian mentioned, there's also a level of complexity. And with the advanced CMOS technologies that we have today, we can already fabricate devices that resemble this level of complexity of our human brain, which is quite amazing. So let's talk about bioelectronics. So when we talk about bioelectronics, we are talking about the study of how electronics can interface with biology or with a living system. And this started or originated more than 200 years ago, but it was only in the 1950s when it became very important for the field of medicine because of the invention of the first pacemaker. And from that, there have been many developments of medical devices that can impact medicine. And if we think of the human nervous system, what we will actually find is a very complex set of electronic pathways. So what an electronic or bioelectronic device is going to do is enable a doctor to interface with these pathways. And this can be done, for example, to reduce a patient's pain, to manage disease, or going to an extreme to help a patient to control a mechanical device just with their mind. So there are many, many applications and many type of devices that have been evolving and being invented as we speak. So let's go a little bit to the basics. So how do we interface with biology? We can do this in two different directions. In the one hand, we can sense, we can read important information of this living organism for different purposes. For example, we can try to understand how it works. We can try to diagnose a disease by reading this information, or we can try to study or monitor a certain disease that is already there. So that's what sensing is going to help us with. We can also actuate or write into this living organism. This can be done, for example, to change or modify a certain behavior, a certain function, or even to treat a disease or an illness without the use of the most standard drug treatments. So we can use then this biology interfacing or bioelectronics for many different purposes. What is very important is for these two directions or of interfacing, we need to be in contact with this biology without damaging it. That means that all the materials and all the components that are part of this contact interface need to be biocompatible. Biocompatibility means that a material is not toxic, that is not causing any adverse effect to this living organism, even when the materials are in contact with it for long periods of time. So this will require also special materials, special fabrication processes, and those are actually also subjects of research in material science. But of course, we are engineers, electrical engineers, but we also need to be aware of what is the challenge on the material science part. In this talk, I will be focused only on the sensing part. Due to time, I will focus on how we will going to read these signals from living organisms or biology. And this can be done with three different methods as shown here. We can have electrical interfacing with this biology, or a chemical interfacing, and there's also some optical methods to interface with biology. In the electrical method, normally you will have metal electrodes or polymer electrodes that are in contact with the body or with biology in order to read, for example, vital parameters such as your heart rate or respiration, but you can also read specifically electrical signals that are generated by a certain type of cells that are called electrogenic cells, that, for example, cardiac cells or brain cells are electrogenic cells. We can also use electrochemical transducers in order to capture chemical elements from body fluids, for example, from sweat or from tears. These body fluids are a rich source of important biomarkers, for example, ions, molecules, and proteins that can give us very medical or clinically important information that can be used for the treatment of some metabolic diseases such as diabetes. And finally, we can also have optical methods to obtain important information from a body, and this includes not only that very well established imaging techniques that requires external equipment such as microscopes, but also some wearable technologies that allow us to sense, for example, blood oxygen levels, blood pressure, blood flows. And an example of these sensors are already included in, for example, your smartwatch. Those are already consumer electronic products that include some of these wearable sensors. So they are very well established already. So for this talk, I will be focusing then on the electrical readout. This is a very well established method because it's the easiest to interface with the living organism. This will only require certain materials for electrodes, while for the others there are more complex interfaces that need to be developed, and that's why electrical readout has been evolving or has evolved more quickly. So let's talk about what do we measure exactly. So when we have a set of electrodes in contact with your body, what are the signals that we can measure? And I have here a few examples. For example, if you have electrodes in contact with your chest, you can read electrical signals from your heart. This is called electrocardiography. And it's a very well-established technique, not only for medical devices, but also for consumer electronics. We can also have electrodes that are inserted in the muscles in order to read electrical signals that are normally triggered by the nerve stimulation of this muscle. And this technique is called electromyography. And finally, we can also read electrical signals from your brain. And for this, there are different techniques to do so. Very small here, but if you place electrodes on the scalp, you can read brain activity, and this is called electroencephalography. If you implant the electrodes on the surface of the brain, so a little bit more invasive, you will read some signals that they call electrocorticography. But we can also implant electrodes deeper in the brain in order to read more detailed neural signals that they call action potentials and local field potentials. When we look at all these signals, they have some differences, but also some similarities. And some of the properties that we can extract from them are shown in this plot. On the one side, it's very important to know what is the frequency component of these signals, and also what is the signal amplitude. So some of them will have a smaller amplitude, larger amplitudes, or lower frequencies, higher frequencies. But in general, these signals are actually very small signals. So they can go from a few microvolts to a few millivolts. And they are also very slow signals. So they can start from less than 1 hertz to maximum 10 kilohertz. Although for people in this field, they will think 10 kilohertz is your high frequency signals. But when we go later to RF, this is actually all considered DC. But what is important is very, very low frequency. So because of those properties, there are 3 problems I want to talk about that are very important for biomedical application. And this first problem is electrical noise. So what is noise? Noise is an unwanted disturbance in an electrical signal, and it affects all passive components that are resistive and also all active components. So if we think of a resistor that has 0 current flowing through it, and you measure the voltage across its terminals, you will expect that the voltage should be 0. But when we measure with an oscilloscope, you will actually see a voltage fluctuation around these 0 volts that is kind of random. This is what we call thermal noise. So thermal noise is generated by random thermal motion of charges or charge carriers. And it is not possible to predict the voltage noise at a given point in time. But what we can predict is what is the average power of this noise. And as given by this formula, this average power will be proportional to the temperature, to the resistance, and to the bandwidth of integration. So here I have a little example. So if you have a 470 kilo ohm resistor at room temperature, you will measure a thermal noise of 12.3 microvolt RMS in a 20 kilohertz bandwidth. So the noise of a resistive component will be in this microvolt range. And this will actually be important because your level of signals are shown in my previous slides are also more or less in that level. Another type of noise that affects our designs and that is present in all active devices is called flicker noise, or also 1/f noise. And although the cause of this noise is not well understood yet, at least fully, what is well known is related to imperfections of crystalline structure of semiconductors. And this noise will vary from technology to technology. So there will be certain technologies of foundries that are optimized for low noise, so that achieve a better, let's say, perfection in this structure. So this noise needs to be characterized always per a specific technology. Although there are other sources of noise or electrical noise, for biomedical application, thermal noise or flicker noise are the most important ones. So I will be talking in my rest of the presentation about this type of noise. So to understand a little bit better the properties of these two types of noise, we need to look at the noise spectrum. The noise spectrum is a plot of your average noise power at each frequency. So if we look at the spectrum of thermal noise, you will find that this spectrum is rather flat. So the noise is more or less the same at every frequency component, and because of this, it is also called white noise. Instead, if we do the same plot for the flicker noise, it's not longer flat, but it will have like a 1/f roll-off, a certain shape, and that's why they also call it 1/f noise or pink noise. So these type of noises are different in properties. The flicker noise, what is important is for the lower frequencies, it can be very high. For the high frequencies, it's very small. So for example, for RF designers, they don't care anymore about this flicker noise. They are in very high frequencies. But for all low frequency applications, and that go for biomedical circuits, also for audio circuits, flicker noise is very important. So if we look at the small signal model of a transistor, we can find that you will have passive components such as resistors and capacitors, but you also have some active components that will be modeled by your current sources. So it is actually expected that this component, a transistor, will generate both thermal noise and flicker noise. So the blue here represents your thermal noise source, the pink your flicker noise source. If we look at the spectrum of noise of a transistor, it should look something like this. In your lower frequencies, you will be dominated by your 1/f noise, while in your higher frequencies, you will be dominated by your thermal noise. And there is a point in frequency where these two noise components will coincide, and this is called your corner frequency. In design, for certain applications, you are trying that this corner frequency is as low as possible, and there are many techniques to do so. Why do you want that? Because you will reduce this contribution of 1/f noise that is actually quite large for a certain frequency portion. So why is this so important? Why I'm talking about this electronic noise? So if we plot this noise spectrum that I just showed you, that represent the noise of a transistor, actually also the noise of an amplifier in general, and we plot on top of it your frequency band of biopotential signals, you will see that these biopotential signals will coincide very much with a very big portion of your 1/f noise and also a portion of your thermal noise. So biopotential signals will always be affected by those by the two types of noise. And it is very important that when you design a biopotential amplifier, you need to minimize or make sure that you mitigate the two types of noises. So let's see here how an amplifier can affect then the readout of your signal. And again, we are here in the analog domain, so your information is in your amplitude. Your information is also in your frequency components. So everything that affects those parameters will distort your signal. So you are not able to obtain the information you want anymore. So if you apply a very clean small signals that range from microvolt to millivolts to your amplifier through an electrode, and your amplifier is also generated noise in the microvolt range, what you will have at the output is a very noisy analog signal that is amplified, but where your information in amplitude is already somehow corrupted by this noise. So how can we mitigate this? You can think, for example, if you have here your amplifier with noise, you know that your frequency spectrum will look like this. You have your 1/f noise, your thermal noise, and you think we have one very easy method. I will apply a low-pass filter to remove part of this noise. You can indeed remove part of the low-frequency noise, and you can remove a lot of your thermal noise. But you will also have a noise component in your band of interest that you cannot get rid just by filtering. So in the end, you will get, a more clean version of your signal, but maybe this is not enough for the specific application you need. So what else can you do? So instead of doing filtering, you can think of a technique. How can I design my amplifier such that instead of generating this large noise, you can generate a much smaller noise? And there are many circuit techniques to do that. You will find books, you will have papers, and this is a subject of research, very active still. Even in this conference, you will find presentations and papers that are related on how to design a better amplifier for biomedical applications. And normally, typical techniques to achieve low noise may include increasing your transistor sizes, or may include increasing your bias currents. So those two things you can do by default as a technique to achieve this very clean output signal. But of course, you notice here that there is already a trade-off that you will have to go through a designer, which is represented here. So in order to design an amplifier with low noise, you may need to sacrifice your area because you need bigger transistors, or you need to sacrifice your power because you need a higher bias current. So this is the most difficult trade-off that a biomedical circuit designer will have to confront every day in a design. How to solve that trade-off, of course, depends a lot on your application. There is not wrong and right always here. So to give you an example, in applications where you want to have many amplifiers to read many electrodes in parallel. This is important, for example, for neural interfaces. You want to record as many signals as possible at the same time. So you want to have many amplifiers. And here, area and power are going to become your most important parameters. So here you may be willing to accept a little bit higher noise just to make sure that you can pack as many amplifiers in a single chip without making it super big or super expensive. So this trade-off then will always come back, and when you see a paper in a conference, you will always have to make a choice of what is, how are they going to solve this trade-off. Let's talk a little bit about this interface with biology. So we have an electrode. I mentioned this can be metal, this can be polymer that is going to be in contact with your biology. And the signals that are captured by these electrodes, let's talk about voltage signals, are going to be amplified and further processed by your integrated electronics. But actually this electrode is a very important component in the whole system because it's also going to determine your signal quality. Not only because the electrode itself is a resistive element, it's going to generate noise, but also because it's normally in contact with a wet environment. Why is it wet? Because normally electrodes will have, for example, a gel when it's applied on the skin, or is in contact with sweat, or is in contact with body fluids when it's implanted in the body. And because of these fluids, there will be some electrochemical reactions happening in that electrode interface. So when we look at this interface, we can talk about an electrode-electrolyte interface. Normally, these fluids are kind of saline solutions, and you will create some electrochemical reactions in the interface. And you can think of this like a little battery, so in chemistry. You can model this interface in terms of electrical components to do your simulations, and very simple electrode model will look like this. You will have in the right side all these passive elements that are going to represent, on the one side, some of them represent the intrinsic properties of the electrode material, so they depend a lot on which material you choose for your electrode. Other components will represent how big or how small your electrode is, so it's an extrinsic property of the material. But a very important component here is this voltage source. So if you think this as a micro battery, you will generate a very small offset in this interface. It's a DC offset, which is called this half cell potential. And this is a DC voltage that will depend, again, on what kind of material do you use for this interface. So if we have an electrode of a certain material, you connect it to an amplifier, you will actually have a model like this. You will have a voltage source. This is source representing your half cell potential, and you have an impedance that are your passive components. And this is interfacing between your biology source and your amplifier. What is very important here is this half cell potential. Depending on the electrode material, it can be tens of millivolts, or it can be even hundreds of millivolts. It can be negative or can be positive. All that depends on the material. So for certain applications, you may want a material that gives you a very small half cell potential, but you may not always have the capability of choosing, because some of the materials can be also good for other type of purposes. So let's look at the spectrum of this impedance. So if we plot the passive component of this impedance, it also has a 1/f behavior, where the impedance is much higher in the lower frequencies, and they are very low in the high frequencies. So if we think at DC, so of course, this is a plot in logarithmic, doesn't show you what is your impedance at DC. But at DC, this electrode impedance can be very large. If you see, that will continue rising, there will be some saturation. And let's say, depending on the electrode type, the size, it can be maybe in the gigaohms. So we are talking about very, very large impedance values. If we model this at DC, so you will have your electrode impedance at DC, but it will be received by an amplifier that is also not ideal. So you will have also a certain input impedance at DC that normally you also expect it very high. So this half cell potential will go through a voltage division here, and the voltage that is seen by this amplifier after the voltage division is what they call the electrode DC potential that I mentioned here in the title. This electrode DC potential is a big deal for biomedical applications because it will complicate a lot how you design your amplifier, and I will be talking about that later. What is important is that this electrode DC offset is then the result of this voltage divider of your half cell potential and how high your input impedance is at DC in your amplifier. So if you look at this formula, something that you can think immediately, if I want to reduce that electrode DC offset, then I want a very small impedance at DC. And yeah, that can be true, but at the same time, you will see later in my presentation, you also want a very high input impedance at AC. So achieving this is not straightforward. Not necessarily that this is the solution to the problem. So let's understand a little bit why is this electrode DC offset a problem. So again, you have your electrode, it has a half cell potential, it has an impedance, and your input amplifier has also an input impedance. So if you have your a small biological signal connected through the electrode, what the amplifier will see at the input is a combination of the small biological signal and your electrode DC offset. If we plot this in time, the input will look something like this. You have your electrode DC offset is maybe tens of hundreds of millivolts, so it's much higher actually than your small biological signal, and you have the signal on top. So if you will amplify this signal, it goes through your amplifier with a gain of A. If you amplify these two signals at the same time, you will be amplifying both your offset and you will amplifying your AC biological signal. But this can work in an ideal amplifier. In a real amplifier, you will actually have what we call a voltage supply. Voltage supply will limit what is the output swing, what is the maximum voltage, minimum voltage that you can see at the output of your amplifier. So if you consider this supply voltage, what will happen at the output instead of the signal that is shown here is what we have here. You will start clipping your signal, you will saturate your amplifier because the amplification is too large for this electro-DC offset. So we actually don't want to amplify the offset along with the analog biological signal. So ideally, what you would like to have is more in a scenario like this. You want to make sure that you only amplify the analog signal and that this is fluctuating along a predefined voltage that is normally your mid-supply. You want to have it mid-supply because then you have swing above and below equally so that you don't saturate your signal in any of the directions and you can apply the maximum gain. So this is the best case scenario, but this implies that you need to get rid of your electro-DC offset before or during your amplification. So how do we do that? So if we want to remove this offset, you basically need to implement a high-pass filter. The challenge of this high-pass filter is that, as we mentioned before, the signals of interest in biomedical signals start in a frequency that is below 1 Hz. So you want to reject everything that is below a very low frequency that is below 1 Hz. And implementing this won't be easy, and it will be describing that. But let's say this is the filter behavior that ideally you would like to obtain. And to implement this on chip, there are different methods. And here I'm going to show 4 examples of how can you implement an active filter on chip using both passive and active components. So we have at the first example, you have a capacitor resistor filter, so an RC filter that is going to remove this offset, and then you go to your amplification stage. This amplification stage can be both closed loop or open loop, but here is shown open loop. The next example, it uses an AC couple, so your capacitor will be also in your input, but here the filter is implemented in the feedback loop of your amplifier instead of before the amplifier. And here the gain will be determined by the ratio of these two capacitors. In the next example, this is a different implementation because instead of implementing a high-pass filter, you implement a low-pass filter and you subtract this low-pass filter version of your signal from your input signal so that the amplifier only amplifies this high-pass filter version. And the same happens with the next one. So you implement a low-pass filter in the feedback loop, and this version of the low-pass filter signal is subtracted from your input in order to create a high-pass filter. So these are 4 ways. There are many other type of implementations of active filters, and you can find those on textbooks, and probably you will see it in your courses. What is important here is that there are many different aspects of these 4 circuits that I want to highlight. For example, in this 4th circuit, it is important to notice that your signal is fed directly to your amplifier. So this will give you the highest input impedance of all the other implementations. This can be important for also signal integrity. I will explain that later. Another observation is that in these 2 examples at the bottom, the input signal is indeed fed to directly to one input of your amplifier, which means that this input of your amplifier will see not only your biological signal, but also this electro-DC offset will be applied directly to that input. This can have several problems. For example, if this electrode offset gets very large or gets negative or positive, then your amplifier needs to be able to deal with that offset without going into linear region or without saturation or without affecting the differential pair. And this is not always evident, especially because electrode DC offsets cannot be always predicted very well. They can change over time depending on the conditions, on the temperature, or because of the gradation of the materials. So you cannot guarantee that your amplifier will always work if you apply the electrode DC offset directly. Instead, if you look at the top architectures, they are AC coupled, which means that you have a capacitor that is already eliminating this electrode DC offset before it reaches the input of your amplifier. So you have full control of what is the voltage that is connected to your terminals, to your amplifier terminals, and you can make sure that that voltage is within the ranges that your amplifier can tolerate. Another important problem here is how do we implement these resistors and capacitors in an on-chip implementation. So if we think of the values, typical values that you can put in a capacitor without being excessively large, is maybe in the picofarad range. That means that if you want to implement this less than 1 Hertz frequency corner, we will need resistors that are higher than 100 gigaohm. This is actually impossible to implement on chip, and I will give you later some insights about how people try to implement this on chip, but it's certainly a challenge that also the designers need to deal with. And I want to then describe now our third problem, that is the electrode impedance itself. This electrode impedance, as mentioned before, if you look at the spectrum, can be very large in the low frequency signal, in the low frequencies, and very low in the high frequencies. And if we put our biopotential frequency range on top, we will see that during that whole range, this impedance varies a lot. So when we think also of the interface, not in DC as we did the analysis before, but now let's think AC. So you have your biological signal connected to an electrode, and this is also received by the input impedance of your amplifier. So the same that happens with your half cell potential that generates a electrode DC offset, you also have a voltage divider for your input signal. So your input signal will actually also be attenuated by this voltage divider caused by the electrode impedance and the input impedance of your amplifier. So what this voltage divider is shown here, but in this case, we don't want to attenuate the input signal because that actually represents or end up in a higher noise. What we want is that this attenuation is very small. So in the application, it is acceptable that this attenuation is lower than 10%. This is just a limit. It can be, of course, better, but let's say this is what is considered a worst case scenario, that your signal gets attenuated by 10%, which also means that your noise degradation or the noise degrades by 10%. And we want to achieve that then that your input impedance of your amplifier is at least 10 times higher than the electrode impedance, and very important, that needs to happen at every frequency point. And although for most amplifier designs, this may not be a problem, actually when you start applying techniques in your amplifier to reduce noise or to eliminate electrode DC offset, you will end up in situations where achieving this condition is not so straightforward. And I put an example. For example, to mitigate 1/f noise, one of the techniques is to do chopping at the input. What chopping is going to do is to make your impedance very low and very flat. So it will be okay, it will be higher, 10 times higher for certain frequencies, but in the low frequency components, you cannot meet that requirement anymore. So this is then an important aspect that you also need to take care of during the design of your amplifier. So how to achieve this high input impedance? I already showed an architecture that achieves the highest possible input impedance, that is applying the signal directly to your amplifier. Although that gives you the highest input impedance, your amplifiers needs to be able to deal with your electro-DC offset as well, so you need to take it into account. Alternatively, you have the most common architecture used in biomedical sensing, that is the one with AC coupling and a feedback loop with your high-pass filter. And in this case, you can also achieve high impedance, but this high input impedance is inversely proportional to the input capacitor. So if you want a high input impedance, you will also require a small input capacitor. And there comes, again, an important trade-off that you will need to solve. On the one side, you want a high input capacitor because that will give you a higher gain, and because a higher gain will also give you a lower noise. But at the same time, you want a smaller capacitor because that will give you a high input impedance and it will make your circuit smaller. So this is again a trade-off that you will need to solve as a designer based on the specific application for which you are building your readout. So that takes us, we saw 3 different problems that affect biomedical circuit readout. And what are the specifications then for an amplifier for this, to be able to read these signals? We need an amplifier that gives us low noise, that can reject the electro-DC offset, and that achieves high input impedance. Those are the 3 basic things that you always want. Depending on the application, you may want also some requirements. You want your circuit to be small as well, especially if you plan to do a massive readout of many signals in parallel. You want to have low power. You may want also good linearity and low input leakage. But as mentioned before, there are many trade-offs here between all these requirements. So you will have, as a designer, have to decide what is the best choice for the specific application. And maybe before we continue, I will pause here to see if there are some questions about this first part.
Hello. I was interested. You mentioned that the electro DC offset is variable. So how do you deal with rejecting a variable DC offset?
Yeah, so the rejection of the DC offset, well, the most common architecture is to have that capacitor. So having an AC coupled architecture is probably the most straightforward, is kind of for free because a capacitor doesn't require power. And it requires certain area, but at the same time, when you implement that capacitor on chip, it's normally a metal capacitor. So if you implement that capacitor, for example, as a mean capacitor, that's the capacitance between 2 metals, you can place it on top of your active circuit. So in principle, it doesn't consume area. So it's kind of for free technique. But there are many other techniques. There are also some disadvantages on having that capacitor. For example, indeed, if you want a higher input impedance for certain applications, that's very important. And a capacitor won't be good enough. So there are other people implemented, for example, DC servo loops or other feedback techniques that gets very, very complicated in implementation. But for some applications, that's worth because it achieves the performance that is wanted.
Thank you.
So for this, we're using CMOS for our gain and filters. How does that compare to using BJTs instead?
That's a good question. BJTs, yeah, I think we haven't used that for a while. A very important difference with BJT, and I'm actually not talking about that in this presentation because of time, but the last point, low input leakage, is also a very important requirement for this application. And with BJTs, the difference of CMOS is that you do have an input current that makes part of your transistor operation. So in CMOS is actually ideal that your input current ideally is almost zero, but of course you still have leakages in smaller nodes, but this current at the input is not tolerable in many applications.
Okay.
Good. Okay, so let's continue a little bit. So I explain you then the basics. What are the three main problems or amplifiers? What are the specifications? And I want to show you now how is a complete readout looking like. So first, you not always have one electrodes, but normally you want to have a differential amplification. So you have a second electrode that is your reference, and you are going to always measure what's the difference between your reference electrode and this recording electrode. So this difference is amplified by the low noise amplifier. That's what the specifications that we discussed before. Then you will require a filter to set your signal band to limit your low frequency, to limit not only the low frequency component, but also all the high frequency signals and noises that you want to reject. You may want to have a programmable gain amplifier. This is optional, but many readouts will try to have an amplifier that gives you some flexibility on how much do I need to amplify my signal in order to make use of the full input range of your analog to digital converter. So this can be important, for example, when you are not sure what is the amplitude of the input signals, and normally that's the case because that will depend on where do you put your electrode, what's the size of material or properties of this electrode. So you may want to have this programmable gain amplifier. And the last part, which is very important, is the conversion from analog domain to digital domain with an analog to digital converter or ADC. And this is important because, as Ian mentioned in the previous talk, there are many things that you can do in the digital domain that can bring the application a step further, doing a lot of signal processing, a lot of compute. That can also help you, for example, to close the loop, to decode, to understand what are those signals that you are recording with your readout. So if you look at this chain, actually the low noise amplifier is probably the most important component that is going to determine your signal quality. It's going to determine your noise. Most of your area and most of your power are also coming from this amplifier, because to achieve low noise, you need to put a lot of area and a lot of power. So this is a component that you want to optimize as much as possible to achieve the performance that you need. The noise of the other stages normally is not so important because when you refer all the noise to the input, they will always be divided by the gain that you apply here. So if you apply a significant gain, you can make sure that the noise of the next components don't have a big impact on the overall noise of the system. And of course, a very important component is this ADC. The ADC is going to determine also your signal quality in the digital domain. And the most important parameter here to choose is what is the how many bits this ADC needs. And this quality, this number of bits, or how many levels do you want to quantize your analog signal, will be determined by the signal-to-noise ratio that you achieve already at your input. So you want to design your ADC in such a way that the quantization noise that is going to add is not significant, that it remains lower than your other noise sources, but you also don't want to over-design this ADC, because over-designing, it becomes very expensive in many means. The area and the power of an ADC are actually exponentially proportional to the number of bits. So adding an extra bit is actually very expensive in area and power. So you just want to have enough, but not more than enough. And it also, in the digital domain, it also becomes expensive because the more bits you have, the more computation and the more power you need to process these output bits. And especially if you have many of these parallel channels, that can become also a bottleneck, a very high data rate that you don't want to deal with. So optimization of the ADC resolution is very important. I will be then giving you some examples of what's the real implementation of this low noise amplifier in transistor level. And here I'm showing you a real implementation of this amplifier that uses this architecture that I showed you before, that is AC coupled. You have your high-pass filter implemented in the feedback loop. But here I'm showing also that you have this reference node. So your amplification is differential on the input, and you want to make sure that your negative path is similar to your positive one, just for a matter of mismatch. So you also have a high-pass filter implemented here. So you have AC couple. It can reject your electro-DC offset. As mentioned before, you can achieve a high input impedance if you keep, for example, this feedback capacitor small and you don't implement a large gain, then you can achieve a high input impedance. It can be pretty much low power, and it can be a small area as well, of course, if you know how to implement this resistor on chip. And to give you an example, an on-chip polysilicon resistor with the best cheat resistance can be around 1 kilo ohm per square. And if you need 100 gigaohms, you will need around 100 millimeter square of chip size. So that's a 10 by 10 chip that only has one resistor. But of course you need two just for this amplifier, and maybe you want tens of amplifiers, maybe hundreds of amplifiers. So this is of course not realizable on chip. So what do people do? So one popular technique, and this is not the only one, is a technique that is called pseudoresistor. This is basically a CMOS transistor, normally a PMOS, that is connected in this diode configuration. So you have your gate connected to the drain, your bulb connected to the source. And because of this, it is actually biased in cutoff in this region that you have here. In this region, this relationship of current versus voltage is very particular, because for a very small change in current, you have a huge change in voltage. So it's actually the equivalent of a very huge resistor. So we can implement some sort of a resistor value that is higher than the 100 gigaohms, even a few teraohms. And what is very important and very beautiful, it can be done in very small area. We are talking here maybe even 1 micrometer square. And also you don't require any power, so it's very cheap in many ways. But of course, things are not as great as that. You have a lot of non-idealities of this component that you will have to know if that's acceptable for your application. For example, it's a non-linear component, meaning that the resistance of this element will depend on what's the voltage across the terminals. So it's not the same for a small voltage that for a large voltage. So it's not ideal for applications where your resistor will see large voltage swings along the terminals. And it also varies a lot with process variation, so and also with temperature. So it's very difficult to predict the exact value of this resistor, but still, if you have enough margin in your design, for example, you design for less than 1 hertz, but you don't care how low it can go. It can be 1 millihertz, and it can go to 1 hertz. For you, it's the same. Then this can be acceptable, but you have this uncertainty, and that will affect also how you design this element in your circuit. Now, another example, how do you actually define this op-amp or your differential amplifier that goes into this low noise amplifier? So here I have the most simple example of a differential amplifier is 5 transistor amplifier. If you think this is a transistor as well, you have a differential pair that is going to do your signal amplification. together with an active load. I have drawn here PMOS input transistors. You can do exactly the same just with NMOS, but it will look, so if you invert this drawing, you will have also the same configuration for NMOS input. And I tried PMOS is because in biomedical applications, PMOS transistors normally have lower flicker noise in general. For most of the CMOS technologies, maybe there are a few exceptions. And that's why most people will choose to have PMOS input. Also, in biomedical applications, you are not after a speed. Normally, an NMOS transistor will be faster, but speed is not what we are after. So in this case, your noise will be generated by all these 4 transistors that you have here. And you may want to design your amplifier such that the noise is actually dominated by your input transistors. How do we achieve this? Normally, some design techniques, and this is also textbook, you will find that a technique to improve the noise of your input pair will always be to increase your GM. Increasing a GM can imply 2 things. One, you may want to increase your bias current, and again, increasing the power. Or you may want to have very wide transistors. That also implies large area. So there is this trade-off that I mentioned before. You may want to have both. That depends on your application. To minimize thermal noise of this active transistor, you actually need the opposite. You want a smaller GM. This is very difficult to achieve when you have a large current. You want the large current for your differential pair, so those things are already conflicting. So there are many techniques to let you achieve this. So there are plenty of techniques for noise optimization of an OTA. These things that I'm mentioning now are just the basics. Large GM for the differential pair, small GM for your active components. This is just the basics, but there are tricks and there are many techniques that help you to deal with these difficult choices that you need to do. Good. So now that we know what the total chain is, for certain applications, we also want to implement multi-channel readout. And as I explained before, an example are neural interfaces where you want to record from many brain regions at the same time with different electrodes. And that requires that you also design an amplifier or a readout that can allow this parallel readout of signals in an efficient way. So how to do this? I will not go through the details, but there are many ways in which you can parallelize your readout, many ways to optimize the area and power, and that will be always a trade-off. What is important here is that for applications where you want many parallel readouts, area and power will always become your 2 most important challenges. So there you will be willing to sacrifice a bit of your noise if that's required, but to be able to implement this on chip without having huge chip sizes, because that's also important in biomedical, especially if you want to have a small implant. You cannot have a chip that is very large, and you also don't want a chip that consumes a lot of power. For an implant, you also may want to power this with a small battery or an implantable battery that you don't want to change very often. So we are talking about levels of power here that need to be really very small. So we are trying to push the limits of these 2 things very much. And that's all about the research of biomedical circuit is indeed how do we push these limits further. And you will find papers, if you stay for the conference in the biomedical session, where you will see people trying to break the limits. There are a lot of innovations that are required that also you can combine with digital design. People that say, okay, instead of having all that chain of amplifier, filter, programmable amplifier, ADC, why don't we just do an ATC that capture the input signal and we get rid of these analog circuits? That's also a very strong domain now in biomedical circuits, how to design, they call it direct to digital interfaces, because they are after optimization. So how do we go minimalistic, throwing up all these unnecessary blocks and trying to create more efficient ways of interfacing with biology? And to finalize my presentation, I wanted to show you a real example of a biomedical device that is used for brain implants. And in this case, it's a chip that have a very peculiar shape, and this is called a neural probe. A neural probe is a device that have these kind of implantable needles, and each needle can have many tiny electrodes that are going to record neural signals at different locations of the brain. Why do you use neural probes? Basically to study brain behavior. There are many things that we still don't understand about how our brain works. And the only way to understand is to be able to sense as much as possible from it. So you want to record these specific neural signals, action potentials and local field potentials, with a lot of detail in order to understand how those signals correlate with certain behaviors, with certain functions. So when we make decisions, which part of the brain are actually active and how. How do brain signals propagate? How do cells in the brain or neurons communicate with each other? So to study all that in detail, you need devices that are able to penetrate the brain tissue and that are able to capture these brain signals with a high density and high accuracy. So this is one of such devices. And if you have all these electrodes integrated in an implantable shank, you can record this with a readout that will look very similar to what I just explained you. What is different in this architecture is that you have your amplifier and filters, but instead of having an ATC for every channel, you want to multiplex several of these analog amplifiers into a single ATC. This is a way, for example, to do optimization of your area and power. So playing with time division multiplexing is also important, and there are many ways to do this optimization. These circuits can become very complex. You can integrate many things on chip. You want to integrate your power management, maybe some digital control, some digital signal processing as well. So this become what they call a system on a chip. So a very complex chip that can do all the functions that are required on the chip itself. And after fabrication, you can have a chip that looks like this. Instead of the traditional rectangular chip, you can do special fabrication processes in order to have these implantable needles that are very narrow. It's like the width of a hair. And they are also very thin, and they can penetrate brain tissue without causing much damage. And that's very important. And these probes can be implanted in the brain in order to record many brain signals at the same time. This is an example of a paper that shows they could measure many of these action potentials in order to study how certain brain regions collaborate together during a function. Good, so I finish here my presentation. As a summary, I want to highlight what are those insights that I wanted to bring today. On the one side, we have biopotential signals are very small, very low frequency. And because of that, it gets affected by several known idealities or issues that are happening in the electronics itself. We have the electrical noise, thermal and flicker that is in the order of microvolts. We have electro-DC offsets that are in the order of tens and hundreds of millivolts. And we have high electrode impedance. And in order to deal with these problems, then we need to make sure we design our first amplifier, the most important one in your readout chain, that is low noise, that can reject this electrode DC offset, and it achieves a high input impedance that is much higher than the impedance of your electrode. And finally, as a designer, you will be confronted with many trade-offs. This won't be easy to solve. Again, you will always have to look at your specific application, but you need to solve the noise versus area, noise versus power, noise versus input impedance, and this won't always be easy, but there are many circuit techniques, many innovations that you can do at circuit level to deal with this. So that's everything. Thank you.